Hi, my name is Alex. Today I'll be talking about machine learning deployment and a little bit about my app called Live Captions. So, what is machine learning and why would you want to deploy it? So, the basic idea behind machine learning is that instead of writing an algorithm by hand, we define the model architecture and we basically just let a computer figure it out. We collect a bunch of training data, we give it example inputs and outputs, and then we get like a big GPU to perform gradient descent. And in the end, we get like a model that has millions, billions, maybe even trillions of weights. These parameters are basically just numbers. And yeah, you can run it with unseen inputs, and hopefully the model will have generalized so that if you give it unseen inputs, it will produce something useful with different inputs. And in some cases, when it comes to natural language or speech recognition, this works better than any handwritten algorithm, and yeah, it would be useful to deploy and make use of it. So there are a few machine learning frameworks, but the most popular these days is PyTorch. It's a Python library where you can define model architectures, you can train models, and you can run them as well. So that's great, right? You can just deploy your PyTorch code to your end user devices. Just tell them to install PyTorch and deployment is solved, right? Well, no. You'll be stuck in Python dependency hell, and users will constantly have issues getting your thing to work on their system. Dependencies will keep changing, and you constantly have to update your stuff to work with, some dependency removed some feature. And not to mention it'll be probably gigabytes of dependencies, and you have no hope of running it on mobile or non-NVIDIA graphics cards. So for mobile and sort of like more lightweight deployment, there's mobile inference frameworks. So these are frameworks that generally you can export a model to their format, and then later from C++, without needing Python or anything, you can just run your model. So there's Onyx Runtime, TensorFlow Lite, which is now rebranded to Lite RT, and there's TorchScript, which I believe is no longer in active development. The general process is that you use a built-in function in PyTorch or whatever to export your model. You give it an example input, so it has to be in the specific shape you want. In some cases, you can get dynamic input shapes to work, but sometimes this can be challenging. So you give it an example input, it runs your model with this input, and records every operation that your model does. So every matrix multiplication, every activation function. It builds a graph from this, and it saves it to a file. And then you can actually look at the file with, you can actually look at the graph with this tool called Netron. Then you write a program that uses the framework to load this file. You can provide it a different input, and it'll run through the same operations and give you an output. So let's talk about Llama C++. It's a fairly popular sort of framework in the local LLM scene. It's what Ollama is based on. It supports different hardware. There's Metal, Vulkan, CUDA. There's AMD's version of CUDA, which is called HIP. It supports state-of-the-art quantization types, and it's being co-developed with GGML, which acts sort of as like the backend of Llama C++. And it has seen a lot of development because, well, people want to run LLMs on their devices, and it's too expensive to buy like a huge GPU cluster. People want to run it on their, older GPUs. So there's been a lot of development. So GGML is a low-level tensor library written in C. It supports various backends. It has minimal dependencies, and it's flexible enough that you can implement any kind of model with it. So not just Llama models, not just language models. And so I became interested in using it for my own models. So what's the difference between Onyx Runtime and GGML? Onyx Runtime has more of an ecosystem, and its whole goal is to sort of simplify the deployment process. GGML is not like GGML's goal is not to like simplify model deployment. It's mainly being built to serve as a low-level library for Llama C++, but of course it remains flexible to other models. And because of being low-level, GGML remains more flexible, whereas Onyx runtime, can make some assumptions about the sort of thing you're trying to do. Onyx runtime does have some strengths over GGML. It supports NPUs a little better. And you also wouldn't really want to use GGML in high-level languages like Python, because it wouldn't really work that well. So just to demonstrate, GGML has a lot of state-of-the-art quantization types that are on the screen. There's K-quants, like Q-quants. You can go all the way down to like 2-bit, or even, I think, 1.58-bit. There's importance matrices, which sort of figure out which weights are more important so that it can preserve the quality of your model a bit better when it's quantizing. And because it's mainly being used to run LLMs, there's been a lot of effort spent to make the stuff optimized, make it work well. Onyx runtime, on the other hand, is a bit more limited. They have 8-bit quantization and some limited support for 4-bit. I personally think it's a bit stuck in the past. I think they got it working good enough, but didn't spend any time implementing anything cool. So onto what I've actually been working on. I made a Linux application called Live Captions, the Captions Desktop Audio Live. To do this, it uses an LSTM model that runs on your device. And to actually run the model, it currently uses Onyx runtime, as it seemed to be the best option when I was developing. And if we look at the size breakdown of the app, well, the app is over 350 megabytes, and most of that is because of the model. The model is being stored in full precision, and yeah, it's over 300 megabytes. It's not great. So this year I wanted to spend some time to work on this, make it more optimized, make it smaller. And I decided I would try to replace Onyx runtime with GGML so that I could make use of its quantization types. So the porting is not yet finished, but the model already runs, the inference is roughly completed. The model file format will need to change. Currently, I don't really see a clear path to automatic file conversion, but maybe there'll be a way. So what are the improvements from porting over? The model can now be quantized to 6-bit with minimal accuracy degradation. This reduces the size from over 300 megs to 75. It can go smaller too, but I think the accuracy degradation gets worse. But I still need to look into how bad it gets, during edge cases and such. It runs faster as well on my desktop. I think I measured around 5 times faster. On an ARM laptop with Rockchip, it can run 2 to 3 times faster. It can also do batch inputs now, so it can stream multiple streams at once. This isn't a feature in Live Captions, but it's part of the library. And on the Rockchip ARM laptop, it can do 7 streams simultaneously. And on a 7900 XTX, using AMD's version of CUDA, it can actually go up to 256. And I think it could go even further with more optimization. Because it's so much smaller, it opens up the possibility to run it on mobile as well. And building it is much easier now because we no longer have to download Onyx runtime libraries. So should you use GGML for your project? There's a lot of reasons why it might be impractical in your case. I've listed some on the screen, but in general, you could try getting Onyx quantization to work, and maybe you'll see similar gains. You will definitely be saving a lot of time because you won't have to implement the actual architecture by hand. You won't have to actually write all the graph code yourself. It's all automatically converted. And if you're switching architectures a lot, if you're switching architectures a lot, if you have like new architectures coming out and you don't want to update your application every time you release a new one, that's also another strength where Onyx would work better. So let's walk through an example from start to finish. Let's make a toy model that detects if an image is purple or not. Of course, you don't need machine learning for this. You can just write like some code like this. But I'm going to use machine learning just to demonstrate how the process works. So the model is going to be pretty simple. Just look at a single row of an image that's been resized to be 64 pixels in width. So there's a linear layer that looks at 3 channels of a 64 pixel row, reduces it to 64 dimensions. There's a sigmoid activation, another linear, and another sigmoid. So I won't go too deep into training, but it works. It learns how to recognize purple. It's a pretty simple task. So if we want to use Onyx runtime, it's pretty simple. We just call this function to export it. We give it the example input, and then you load it like this, and you run it with a purple image, and yeah, it's 99% sure that it's purple. So we want to do the same thing in GGML. If you're dealing with more complex models, what you might find is that the code is like scattered across different files, especially if you're porting like somebody else's model. You would have to spend a lot of time tracking down like where the actual inference code is and how the inference works exactly. So because of this, I find it most useful to look at all the weights, all the weight keys and their shapes to make sure you're not missing anything. And you can use that to figure out how parts of the model work exactly. And then I would suggest implementing the model in NumPy because it's much easier to debug and figure out what's happening, verify all the numbers are correct. And once you're done with that, you can implement it in GGML. So you can save the weights like this, and you can save it in as a NumPy file as well. So you can load the NumPy weights, and here are all the weights and their shapes. There's 0 weight, bias, 2. Now we just need to figure out what they correspond to. In this case, it's pretty simple. It's just a sequential linear model. The activation functions don't have any weights, so it's just the 2 linear layers that have weights. And yeah, this is how they correspond. With a normal model, you would normally have a lot more weights than this, but in this case, it's pretty small. So to implement it in NumPy, it would work like this. The @ symbol performs matrix multiplication. The .t means transposition. And this is how you implement a linear layer. And then you have the sigmoid, the second linear, and sigmoid again. You can run it, and yeah, it works. You can verify the outputs are correct. Now that we know the model works, we have a working NumPy implementation, we can start porting it to GGML. The first thing we can do is export the model weights to the gguf file format, which is what's used by GGML. It supports storing tensors and metadata, so we just add each tensor and some basic metadata. Now in our C++ code, we can write a structure describing our model. Normally you would have like a hyperparameter structure, but we just skip it. One thing to know about GGML is that the tensor shapes are reversed. If you print that tensor shape in PyTorch or NumPy, it might be like 128, 192. In GGML, that shape would be 192, 128. This is because if you think about it, in other frameworks, they're actually writing it right to left. Like if you add a new dimension, the new dimension would appear on the left instead of the right. In GGML, it's reversed. So if you had a new dimension, it would be on the right. So new dimensions appear on the right side. So some stuff in GGML may refer to dimensions in standard order. So just watch out for like the numbering. So we load our weights. At this time, I think you have to like make a separate GGML context and then initialize the GGF context with that. And yeah, you can check the metadata here, just iterate over the weights in the context. But you could also just get them by name using GGML get tensor. Okay, so at this point, let's implement the actual model calculations. And you might look at the GGML header file and see there are all the corresponding functions. There's GGML molmat, transpose, add, sigmoid. And you could write it like this as like a one-to-one translation of the NumPy code, because everything here corresponds exactly. You know, you're transposing the weight, you're multiplying the matrices, adding the bias. But this is actually wrong, and the reason it's wrong is because matrix multiplication works a bit differently in GGML. So GGML actually does transposition for you, and you should actually specify the model weight first, and then your input tensor second. Since from my testing, this sort of reduces the issues you get when you're dealing with quantization, because I believe the multiplication operations, they require the first element to be quantized and the second to not be quantized. So you then might try to run the model like this. Again, remember the shapes are written in reverse order. So we create our input tensor, we copy the image, we get the result, we sum it because we have 128 columns that we're summing over, and we return the average value. This won't work, it will return 0. The way we're actually supposed to run it is by creating what's called a computational graph. So we create the graph, we run the model then, and then we build the graph by using the output, and then we call a function to compute the graph, and then we can access the result. And this implementation here, it will work, but after a few times it will run out of context memory and stop working. If you notice, we're not actually freeing the graph. And if you look around the header file, there actually is no function to free the graph or even free tensors. And that's a sort of design decision in GGML. The way you're actually supposed to do it is by creating a temporary context with allocation disabled and then create the graph. So in this function, we create a static buffer, and then we use that buffer in this function to sort of initialize the context. And then we create the graph. That graph lives in that static memory. So then we free the context, the temporary context. And, you know, the graph lives in that buffer still. So it's not like dangling memory or anything. It'll just get overwritten on the next run. Then during initialization, we have to create a CPU backend and an allocator. And we call that earlier function we just looked at to get the graph, just so we can reserve memory for it. And then to actually run the model, we get the graph again, we allocate memory for the graph. Then we set all our inputs with the backend tensor set function and get the outputs with backend tensor get. And this will work. It won't leak any memory. It works great. So how do we quantize the model? We will need to quantize our GGF file. Typically in GGML, the way this works is that you have to write your own sort of binary. that loads the GGF, and then it selectively quantizes some of the tensors, not all of them, and then it saves it. And the reason you want to skip quantizing some tensors is because if you quantize your biases or just one-dimensional tensors in general, you won't really be saving any space. You will mainly be losing accuracy, and sometimes you may run into errors because the number of elements is not divisible by some number. So I won't go over how to write this, but I have an example in the repo, which I mainly copied from one of the GGML examples. So if we're quantizing to 4 bits, some basic maths will give us an estimate of 6.26 kilobytes. In practice, it's a little bigger because there's overhead and we're skipping some tensors. But this is already way smaller than the full precision models. So our final program is under 1 megabyte. I believe it's around 2 megabytes if we statically linked everything. So it's pretty small compared to some of the other libraries. And yeah, it works if here it is running a 4-bit model. So how do we run it on GPU? Well, we could replace the CPU backend with a GPU backend like Vulkan, but there's a bit more work needed because we actually need to upload the weights to the GPU. So to upload weights, I made this a little utility. You create a context with allocation disabled, and you call this on every weight. It'll replace them with a blank tensor created in that context. And then you can allocate a backend buffer for that context. And it'll allocate all the memory for those tensors. And then you just have to put the weights actually in there. And you can just do that by calling GGML backend tensor set. We moved the backend and allocation stuff to our load model function. Moved it into the struct just to make it easier. And then we mark all the tensors for uploading. We allocate the backend buffer like I mentioned, and we can then upload all the weights. And yeah, with this, it works. It runs on GPU. One thing to know is that it won't always give you a speed up. Like, there's overhead when it comes to running models, and obviously this one is very small, so you won't really be seeing much speed up from doing this. Of course, your memory transfers will be slower, so whenever you're calling backend tensor get or set, you'll be waiting longer. And some operations just won't work the same as CPU. You may run into errors. This might be either because the backend doesn't support the operation, or it requires the tensor to be contiguous. So you need to add a call to GGML cont to that before calling that operation. So that's the end of the talk. I hope to merge the GGML porting to live captions soon, and hopefully get started on other exciting projects using the April ASR library. And yeah, you can find the example code here, and thank you.